Hello viewers, welcome to today's lecture on flow and error control. In the last lecture, we have discussed about various error detection techniques, and also we have discussed a technique for forward error correction known as Hamming code, using Hamming code. Now, for communication for successful data communication, it is necessary to use some techniques so that data communication can be performed in a reliable and efficient manner. So, in this context, two techniques, flow control and error control, are very important. So, in this lecture we shall discuss about these flow and error control techniques. Here is the outline of today's lecture. First, we shall discuss why flow and error control is necessary. Then we shall discuss the two important flow control techniques, stop and wait flow control and sliding window flow control. And we shall compare the performance of these two flow control techniques, namely stop and wait flow control and sliding window flow control. Then we shall see how we can perform backward error correction using three techniques: stop and wait ARQ, go back N ARQ and selective repeat ARQ. So, we shall consider these three techniques one after the other. And on completion of this lecture, the student will be able to explain the need for flow and error control. They will be able to explain stop and wait flow control technique, how it works. They will be able to explain how sliding window protocol is used for flow control. Then they will be able to explain how stop and wait ARQ works. They will be able to explain how go back N ARQ works, and also they will be able to explain how selective repeat ARQ works, and they will be able to compare the relative performance of these three techniques. First, let us focus on why flow and error control. As I mentioned, for successful data communication, we have to use certain techniques. Now, we know that for data communication, we require at least two devices or two machines. One is sender, another one is receiver. And we require a great deal of coordination between these two devices or machines for reliable and efficient data communication. Let us see what are the constants involved in it. First of all, the one constant is both sender and receiver have limited speed. That means they will require some time to receive data, to process data and to store data. So, some limited, because of limited speed, it will involve some time. Similarly, both sender and receiver have limited memory or storage capability, and usually it is known as buffer, because whenever data communication takes place, usually the data that is being received is temporarily stored in memory or called buffer. So, that capacity is limited. So, under these constraints, the requirements are: a fast sender should not overwhelm a slow receiver, which must perform a certain amount of processing before passing the data onto the higher level software. That means after the data is received, the receiver has to do some processing before it can pass on to next higher level software or store it in the permanent memory. Now, we know that there are different kinds of machines. For example, a server, usually a high-end machine which can perform processing at a higher speed. On the other hand, a client or a receiver can be a little low-end machine, and obviously its speed or processing capability is lower compared to the server. In such a situation, the sender should not at such a rate that the receiver is overwhelmed. So, we have to protect the receiver from being overwhelmed, and for that purpose the sender must send data in a very controlled way, because unless it is sent in a controlled way, there will be overflow from the buffer or information will be lost. That controlled way is known as flow control. That means you will see that the receiver will send some acknowledgement before the sender sends some data. By using that kind of coordination, the flow control, that overwhelming can be overcome, and data communication will take place successfully without any loss of information. Also, another requirement is, if error occurs during transmission, it is necessary to devise mechanism to correct it. We have already discussed the error detection techniques and also one forward error correction technique using Hamming code. But commonly forward error correction technique is not used. The most commonly used technique is that the receiver will check the received data. If an error is found, it sends the information to the sender that error has occurred in the received data. Then the sender will retransmit the data again, and these techniques are known as backward error correction or error control techniques. So, we shall for reliable and efficient communication, we have to perform flow and error control. So, in this lecture we shall discuss about these techniques. First, we shall focus on the simplest flow control technique, the stop and wait flow control. Although this flow control and error control are performed in an integrated manner, but for the sake of understanding, we are considering it one after the other. Usually they are performed in an integrated manner, as we shall discuss later. Now, in this stop and wait flow control, the source transmits a data frame. That means sender transmits a data frame, and after receiving the frame, the destination, that means the receiving end, indicates its willingness to accept another frame by sending back an acknowledgement frame. So, the receiver, after receiving that frame, will send an acknowledgement, and it will indicate that a frame has been received already. So, another frame can be, it is ready for receiving another frame. The source must wait until it receives the acknowledgement frame before sending the next data frame. This is the basic idea behind the stop and wait flow control. Let us see how it really works with the help of this animation. So, here is the sender side and here is the receiver side, and a frame is ready for transmission and it is being sent by the sender. So, it is taking some time to reach the receiver, known as the propagation time, and after receiving the frame, the receiver will take some time to do some processing, then it will send an acknowledgement, and the acknowledgement will reach the sender, and after it is received by the sender will send another frame. So, you see there is a waiting time involved before another frame can be sent. Similarly, after another frame is received by the receiver, it will send another acknowledgement, and after receiving that acknowledgement, again the sender will send another frame, as you can see from this animation. So, here as you can see, between two frames there is a waiting time or wait time involved. So, some time is wasted before another frame can be sent. And this ensures that the receiver is not overwhelmed. So, this is the basic idea behind stop and wait flow control. Let us see the performance of this stop and wait flow control technique. And for that purpose, we have to understand about two important parameters. One is known as transmission time. The transmission time is the time it takes for a station to transmit a frame. It will depend on what? The time for transmission of a frame will depend on the length of the frame, and also it will depend on the rate at which the transmission is taking place. Let us assume the rate is the size of the frame is 10 to the power 3 bytes, that means 1 kilobyte, and the rate at which it being sent is say 10 megabits per second. So, when it is sent at this rate, obviously the transmission time will be 10 to the power 3 by 10 to the power 6, that means 1 millisecond. Now, let us come to the propagation time. The propagation time is the time it takes for a bit to travel from the sender to the receiver, and this time is obviously is dependent on the distance and the speed of the electromagnetic wave. So, depending on the distance, obviously longer the distance, more will be the propagation time. And if, for example, whenever we use satellite communication, then the signal goes from the base station to the satellite and back to the ground station, and as we know, it takes about quarter of a second. And whenever we are using say fiber optic communication, the length of the cable can be very long, and in such a situation the propagation time can be long. And the ratio between the two is known as A. A is the ratio between propagation time by the transmission time. Usually transmission time is normalized to the value 1. So, whenever A is less than 1, the frame is sufficiently long such that the first bit of the frame arrive at the destination before the source has completed transmission of the frame. That means, suppose here is the sender, here is the receiver. So, it has started transmission. Now, in such a situation, you will see before the first bit reaches the destination, the transmission is not yet complete. That means, in this case transmission time is longer than the propagation time. On the other hand, whenever A is greater than 1, in such a case what will happen, this is the sender side and this is the receiver side. Before the transmission is over, that means the transmission will be over before it reaches the other end. For example, the scenario will be somewhat like this. That means, this is the frame, and you see before this end has reached the receiver, the transmission has been completed and it has already taken some time has passed. So, this will be the case whenever A is greater than 1. And depending on this value of A, which is the propagation time by transmission time, it can be shown that the utilization of the link is equal to 1 by 1 plus 2A. So, you see higher is the value of A, utilization will be poor. On the other hand, smaller is the value of A, utilization will be better. So, we can see that whenever we are communicating over a long distance, then there is a possibility of inefficient utilization in case of stop and wait flow control. On the other hand, when the propagation time is small, then the utilization will be better. And this problem can be overcome by using sliding window protocol. The main limitation of stop and wait protocol is that at a time only one frame is in transit. As we know, normally a single message is divided into a number of frames. So, whenever short frames are sent, then the transmission time is small, and that is used so that the error does not occur and various other reasons. So, in such a case the stop and wait flow control will not be efficient. So, when the use of multiple frames for a single message, that is the normal scenario, stop and wait flow protocol does not perform well, as you have seen. The main reason is that here only one frame at a time can be in transit, and that is being overcome in sliding window protocol, as we shall see. And as we have seen, whenever A is greater than 1, then serious inefficiencies result in stop and wait protocol. Efficiently can be greatly improved by allowing multiple frames to be in transit at the same time. That means, before an acknowledgement is received from the other end, if multiple frames can be allowed to be sent, then efficiency can be improved, and that is precisely what is done in case of sliding window flow control. Moreover, efficiency can be further improved by making use of full duplex line. As we shall see, the acknowledgement can be sent from the receiver side along with, as part of a information frame, and that is known as piggybacking. So, piggybacking technique is used. We shall explain about it in details, and which will improve the efficiency of the transmission. Let us see how the sliding window protocol works. Now, first of all, to keep track of frames, we are sending multiple frames. Obviously, unless the frames are numbered, it will be difficult to keep track which frame has received the destination, which frame has not received, has not reached the destination. So, the frames are sequentially numbered, and they are sent, and the sequence, since the sequence number to be used occupies a field in the frame, it should be of limited size. Obviously, the sequence number should be part of the frame. That sequence number has to be embedded, will be one of the fields of the frame, and obviously the number of bits that is added, that is used for representing the sequence number, will be an overhead, and that is why there is some restriction on the number of bits that can be used. If the header of the frame allows k bits, then the sequence number range is from 0 to 2 to the power k. That means, there is a possibility of having 2 to the power k numbers with k bits whenever you are using k bits for representing the sequence number. Sender maintains a list of sequence number that is allowed to be sent. That means, a window is maintained at the sender's end. It is essentially the number of frames that can be sent, say starting with say 0, and then if you are using 7 bit, it can be up to 0, 1 to 7. However, all the this you will see that the window size is usually not 2 to the power k, but 2 to the power k minus 1 less than this. That means, it has to be 1 to 6. And then that means, this is the range of frames which can be sent from the receiver without receiving an acknowledgement. And the sender is provided with a buffer equal to the window size. That means, sender is having a buffer to store all these frames, and then they are sending one after the other. And similarly, at the receiving end, a window is also maintained, but the size of that window is equal to 1. The receiver acknowledges a frame by sending an acknowledgement frame that includes the sequence number of the next frame expected. That means, suppose frame 0 has been received by the receiver, then it will send an acknowledgement like this ACK1. That means, the frame that it is expecting next. So, in this way, it is the this explicitly announces that it is prepared to receive next n frames beginning with the number specified. That means, with this number 1, that means 1, 2, 3, in this way up to starting with 1 to n minus 1 frames to the power k minus 1 frames it can receive one after the other. So, this readiness is conveyed by the receiver. This scheme can be used to acknowledge multiple frames. So, it is not necessary that for each frame received by the receiver, it has to send an acknowledgement. It is possible to send a single acknowledgement for a number of frames. And how it can be done? Let us see. Suppose it has received 3 frames 2, 3 and 4, but withhold acknowledgement until frame 4 has arrived. Now, by returning an acknowledgement like ACK 5 with sequence number 5, it acknowledges frame 2, 3 and 4 at one time. That means, by sending a single acknowledgement ACK 5, it serves the purpose of acknowledgement for 3 frames, namely 2, 3 and 4, and obviously the sender will now transmit the frame number 5, frame 5. And in the receiver, as I said, since the window size is 1, it will require a buffer of size only 1, because at a time it is receiving 1 frame and then passing it on to the next higher level. Let us see how it actually works. So, as you can see here, we are using k is equal to 3. So, our window size is 2 to the power k minus 1, that is 7. So, here you can see 0, 1, 2, 3, 4, 5, 6. This is the window at the sender's end. On the other hand, at the receiver's end, the window is only 1. So, it is now ready to receive the frame 0, and the sender sends the frame 0, and as it sends the frame 0, as you can see, the window is shrinking by 1. That means, now it has got 6 more frames to send, starting with 1, 2, 3, 4, 5, 6. So, when a frame is sent, the window shrinks. On the other hand, as we shall see, when an acknowledgement is received, window is expanded on this side. Now, the receiver side, after receiving the frame, also moves the window from 0 to 1, because now the frame 0 has been received. Now, it is ready to receive the frame number 1. So, frame number 1, as it is sent, again the window shrinks by 1. So, 2, 3, 4, 5, 6. These are the frames which it can now send. Now, suppose the receiver side send acknowledgement ACK 2. That means, it is now ready to receive the frame 2. So, when this is received, as you can see, the window has been extended by 2. Earlier it was ending with 6, now it is 7 and 6. So, again the window is now having 7 frames, 7 numbers 2, 3, 4, 5, 6, 7 and 0, and it will send now the frame number 2, I mean from this end. So, frame number 2 is sent, again the window is being extended to 3. So, in this way it goes on. Now, I mentioned about that a piggybacking technique is used whenever 2 sides are communicating with each other, and another point is the maximum window size need not be equal to 2 to the power k minus 1. This is the limit or maximum size that can be used. However, in practice one can use lesser than that, but in that case the overhead increases. Unnecessarily, if we use more bits to represent the sequence number, overhead increases. So, usually we try to use the maximum number, that is 2 to the power k minus 1, that is the window size. Now, if 2 stations exchange data, each need to maintain 2 windows to save communication capacity, and that is known as the technique is known as piggybacking. How it works? Each data frame includes a field that holds the sequence number of that frame plus a field that holds the sequence number used for acknowledgement. That means, each side will have 2 fields. One field is the sequence number, that is the frame number, and another is acknowledgement number. So, frame number and acknowledgement number, that acknowledgement number is piggybacked as part of the frame that is being sent, and as a result we need not send a separate frame acknowledgement frame for this purpose. So, some saving in the bandwidth occurs in this way, and this is known as piggybacking. However, if a station has an acknowledgement but no data to send, it sends a separate acknowledgement frame. It is not always necessary that both sides will send acknowledgement frames by using piggybacking, because if a particular station has no frame to send, then it has to send acknowledgement frame after receiving the information frames. Let us see the link utilization in case of sliding window protocol. Here the utilization will be 1 if n is greater than 2a plus 1, where n is the window size and a is the ratio between the propagation time and transmission time. Let us take up an example. Suppose we are using k is equal to 5 bit. In such a case, the value of n will be equal to 2 to the power 5 minus 1, that is equal to 31. So this is the window size. Now suppose the value of a is equal to 10, let us assume. So whenever a is equal to 10, obviously the utilization will be, in this case the utilization will be 1, because n is greater than 2a plus 1. A is 10, so 21. So this is greater than 1. So in this case the utilization will be 1. On the other hand, let us assume the propagation time is very long, and as a consequence a is equal to, let us assume 200. That can happen in satellite communication. So whenever that happens, the utilization will becomes equal to 30, that is your n is equal to 31 by 1 plus 400. So you see the utilization is much less in such a situation whenever you are using communication over a longer distance, that means propagation time is long, or you are sending at a very high speed, then also the transmission time will be short. So you see that whenever n is greater than 2a plus 1, in such a situation sliding window protocol is capable of sending continuously almost without waiting, because we have seen that it maintains a window. Before the window is exhausted, all the frames of that window is transmitted, it receives an acknowledgement, and so it keeps on expanding the window in one direction. So in this way continuous flow of traffic is possible if the value of n is chosen in such a way that it is greater than 2a plus 1. So you see that link utilization can be significantly better in case of sliding window protocol. Now let us focus on error control. We shall consider this model for backward error control. Data are sent as a sequence of frames, as you have already seen how it is being done. Then frames arrive at the same order as they are sent. We are assuming that frames are reaching the destination in the same order, because usually we are considering the case where the two nodes A and B are linked by a direct communication link. So in such a situation there is no possibility that the frames will be reaching out of order, it will be reaching in the same order. However, each transmission frame suffers an arbitrary and variable amount of delay before reception. There can be some delay on the path because of some reason. In addition to the above, following two types of errors may occur. Now what can happen? So far we have assumed that when a frame is sent, it is reaching the destination without any error or without any loss. However, it can happen. First of all, let us consider the case of lost frame. A frame fails to arrive at the other side. So how it can happen? Whenever a frame is sent, in what situation a frame cannot reach the destination or it gets lost on the way? One possibility is that there may be some noise, and that noise can be such that it may corrupt to such an extent that information is not recognizable. So a noise burst may damage a frame to such an extent that it is not recognizable at the receiving end. In such a case we may call that the frame is lost. Another possibility is that the frame is damaged. Whenever error occurs and that is detected by suitable error detection scheme that we have already discussed, then we can say that the frame is recognizable, but some errors has occurred, bit errors has taken place. So, in such a case we call it damaged frame. So, we have to take into consideration these two situations whenever we consider the error control. Most of the common techniques for error control are based on some or all of the following. First of all, it uses error detection. What are the components of error control are explained here. First of all, there should be some technique for error detection. We have already discussed about a number of techniques for error detection, such as parity check, cyclic redundancy check, and checksum. One of the techniques can be used for error detection, and normally the cyclic redundancy check is used because we have seen that this is the most sophisticated one and gives you much higher fault coverage. Then it will use the concept of positive acknowledgement. The destination returns a positive acknowledgement to successfully received error free frames. So, that is usually represented by ACK. On the other hand, there can be negative acknowledgement. So, the destination returns a negative acknowledgement to frames in which error is detected. The source retransmits such frames. So, whenever the acknowledgement comes in the form of negative acknowledgement, then the sender has to retransmit the frame. Apart from that, there will be necessity for retransmission after timeout. The source retransmits a frame that has not been acknowledged after a predetermined amount of time. What can happen? That happens in case of damaged frames. A frame is damaged to certain extent, it is not recognizable. So, that the receiver assumes that no frame has come. So, in such a case, the sender will use some kind of timeout mechanism for retransmission. So, these are the basic techniques or components used for backward error control, and these error control techniques are collectively referred to as automatic repeat request ARQ. And obviously, as I mentioned in the beginning, our objective is to turn unreliable data link into a reliable one. As we know, there does not exist any transmission media where error cannot occur. Error can always occur, although the reliability of the transmission media is improving with time. However, there is always some possibility or probability of error. So, in such a case, in the error prone environment, our objective is to perform reliable and communication. That can be done by using these error control techniques. And there are three versions of ARQ techniques. One is known as stop and wait, based on stop and wait flow control. Second is go back in, based on that sliding window protocol. Then selective repeat, it is also based on sliding window protocol. So, these are the three ARQ techniques which are used, and we shall discuss them one after the other. Let us first consider the stop and wait ARQ technique. As I mentioned, it is based on stop and wait flow control technique. The source station transmits a single frame and then waits for an acknowledgement, as we have seen that is done in case of flow control. Then no other data frame can be sent until the destination station's reply arrives at the source station. That is, we have seen that is being performed as part of the flow control. Now, to take care of lost and damaged frames, the stations are equipped with another device known as timer. If no recognizable acknowledgement is received when the timer expires at the end of timeout interval, then the same frame is sent again. That means, after sending each frame, the sender starts a timer, and based on the propagation time, the distance, some time is fixed, and and the timeout time is fixed. And after the timer reaches the timeout, and if no recognizable acknowledgement is received, then the sender will retransmit the frame. That is the basic mechanism. So, this however requires that the transmitter maintains a copy of a transmitted frame until an acknowledgement is received for it. So, we have seen that sliding window was moving forward only after receiving an acknowledgement. That means, for all the frames it receives an acknowledgement, the buffer can be released. That is the basic idea here. However, there is a possibility that acknowledgement frame is also damaged. So, in this case also the sender will time out and resend the same frame. Now, there is a possibility that whenever the acknowledgement is damaged or lost, then the receiver, the sender will retransmit it. So, there is a possibility that receiver receives the same frame twice. How do you overcome that? That can be overcome by using a modulo to numbering scheme. What is done? The frames are sent alternately as frame 0, then frame 1, then again frame 0, alternately this is done. So, if frame 0 is acknowledgement of frame 0 is lost, frame 0 will be transmitted. So, there is no possibility of confusing with the next frame, because next frame will be frame 1. So, by using this numbering, the possibility of receiving duplicate frame is avoided. Similarly, the acknowledgements are also numbered in this way. For example, as an acknowledgement of frame 0, it will be SEK 1, and as an acknowledgement of frame 1, it will be SEK 0, and then again acknowledgement of next frame frame 0 will be SEK 1. So, this is how it goes on, and this is shown with the help of this diagram. As you can see, the here a frame is sent, frame 0, and in response to that the receiver will send an acknowledgement SEK 1, then the transmitter or sender will send frame 1. In response to that, the receiver will send an acknowledgement SEK 0, and after receiving that acknowledgement it will send another frame 0, but these two frames are not same, they are different frames. They are numbered alternately, sequence number is numbered alternately in this manner. And why, you may be asking, why you are using modulo 2 numbering? The reason for that, you require only one bit. So, the overhead is much less here. Only one bit is required for numbering the frames. Now, you see this frame is reached with error. So, receiver detects error in it. So, a NA key 0 is sent, no acknowledgement 0. So, in this, after receiving that, the transmitter will send that frame 0 once again. So, now it receives that frame in correct form. So, it sends an acknowledgement SEK 1, and then the receiver will send, the sender will send the frame 1. So, this goes on in this manner. Now, let us consider the situation when a frame is lost in transit. As I mentioned, a frame may get damaged to such extent that it is not recognizable by the receiving end, and in such a case we call it lost frame. So, we see that frame 0 is being sent to the receiver, and it is an acknowledgement is sent, and another frame is sent, and however this frame is damaged, and as a result this frame is lost, and we can see there is a timer which times out, and after the timeout is reached, the same frame is retransmitted. So, frame 0 is again retransmitted whenever the frame is lost and the timer is after the timeout time is reached. So, we see I have shown only in this case, but it happens for all the cases. Now, let us consider the case of lost acknowledgement. In the previous case we have seen the lost frame, but here we see the lost acknowledgement. So, frame is reaching without any problem, but the acknowledgement is now lost, timer is proceeding, and as the timeout is reached, again the frame 0 is sent. So, this is how retransmission takes place in case of stop and wait ARQ technique. The main advantage of stop and wait ARQ technique is that it is very simple, and also it requires a minimum buffer size of 1, and also the number of bits required is 1. That means the number required for representing the sequence number is 1. So, in both cases 1 is 1. So, it is minimum. However, the disadvantage is that it is highly inefficient use of the communication links, particularly when A is large, because the efficiency will be same as that stop and wait flow control. So, we find that stop and wait ARQ technique is not very efficient. How it can be overcome? Obviously, it can be overcome by using the technique of sliding window protocol for ARQ, and this is known as go back N ARQ. Why the name go back N ARQ is given will be clear very soon, and this is the most commonly used technique. Basic concept is a station may send a series of frames sequentially up to a maximum number. Maximum number is essentially decided by the window size. As we have seen that say you are using k is equal to 3, in such a case the window size is 7. So, the numbers are 0, 1 and up to 7, up to 6. So, so many frames can be sent without receiving an acknowledgement. So, 0, 1, 2 and all these frames can be sent and without receiving any acknowledgement. That is the one idea. The number of unacknowledged frames outstanding is determined by the window size using the sliding window flow control technique, as we have already explained. In case of no error, the destination will acknowledge incoming frames as usual. So, the acknowledgements are sent as usual in the previous case. However, whenever the destination detects an error in the frame, as I mentioned, that negative acknowledgement is sent, which is known as reject frame, REG frame. So, REJ frame. The destination will discard the frame in error and all future frames until the frame in error is correctly received. So, what will happen? The destination will discard the already received frame and it until the a particular frame is received correctly. The source station on receiving an REJ reject frame must retransmit the frames in error plus all the succeeding frames. Let us see how it actually works. So, here it is explained with the help of this diagram. Frame 0 is sent. So, here it reaches correctly. Frame 1 is sent, then frame 2 is sent by the sender, and you can see for all these 3 frames a single acknowledgement is sent as SEK 3. Now, the transmitter is keeping on sending 3, then it is sending 4, then it is sending 5. Unfortunately, the frame 3 has reached with error, and as a result the receiver sends a negative acknowledgement NAK 3, and at the same time what it does, it discards the frame 4 and frame 5. It is not, because it has got only one buffer. So, there is no possibility, since the receiver is having only one buffer, it cannot really store the subsequent frames. If a frame is not received correctly, then all the subsequent frames are discarded. So, frame 4 and 5 are discarded. Now, you see the transmitter will start sending frame 3, 4 and 5. So, you see that is why it is called go back N. So, it is going back to 3 and again retransmitting 3, 4, 5. So, 3, 4, 5 are sent and they are being received one after the other at the receiving end. So, the name go back N is coming from this. We see here, although the transmitter had sent up to 5, it is going back to 3 and again then it is retransmitting 3, 4 and 5. So, in this way it proceeds. Now, let us consider what happens in case of lost or damaged frames. Here frame 0 is being sent, then frame 1 is being sent and frame 2 is now lost. Since frame 2 is lost, and after the frame 3 is received by the destination, it will be discarded because it is waiting for frame 2. The window that it was having was showing 2. So, it can receives only frame 2, no other frame can be received. So, here the frame 3 is discarded. At the same time, it sends one negative acknowledgement NAK2, and after receiving that NAK2, the sender will again send 2, 3 and 4 because it is using go back and ARQ technique. So, how the lost frames are tackled is explained here. Let us see how the lost acknowledgement is tackled. Here we see that frame 0 is sent, frame 1 is sent, it is received correctly, frame 2 is also received correctly. So, it sends an acknowledgement ACK3. That means, it is asking the frame 3 to be sent, and it is lost unfortunately. So, after sending frame 0, it has not received an acknowledgement. So, it keeps on it has already started a timer, and it reached the timeout at this point. Since no acknowledgement is received within this period, it starts retransmission starting with frame 0. So, frame 0, frame 1 and frame 2, these are all sent one after the other to the receiving side. So, this is how in go back and ARQ protocol a lost acknowledgement is taken care of. Let us see the window size limit in case of go back and ARQ. Let us assume full duplex transmission is going on. The receiving end sends piggybacked acknowledgement by using some number in the acknowledgement field of the data frame. Let us assume a 3-bit sequence number is used, and obviously the window size can be up to 8. So, it can be 0 to 7. Now, suppose that a station sends frame 0 and gets back receive request 1, that is essentially this is acknowledgement 1. Then the sender sends frame 1, 2, 3, 4, 5, 6, 7 and 0 and gets another RR1. So, it has received 2 RR1. Now, this might either mean RR1 is the cumulative acknowledgement or all 8 frames were damaged. So, the transmitter will be puzzled. So, if all are damaged and lost, then obviously this RR1 corresponds to the first 0, that means before this the frame 0 was sent, it corresponds to frame 0. On the other hand, if it is not damaged, then this RR1 can correspond to the next frame after this 0. So, this can be either for this or the next frame after 0. So, which one has to be considered, the transmitter gets confused. This ambiguity can be overcome if the maximum window size is limited to 7. That means, if the window size is limited to 7, that means 0 to 6, this problem will not arise. It can be very easily proved. That is why whenever k-bit sequence number is used, the window size is limited to the power k minus 1 in case of go back and ARQ. Let us see the case for selective repeat ARQ technique. In this case, only those frames are retransmitted for which negative acknowledgement has been received, and this negative acknowledgement is referred to as SRJ, selective reject, or timeout has occurred. In either case, only that frame is sent. We have seen that in case of go back N, the transmitter is going back to some previous number and it sends a number of frames which were already retransmitted. That is not done in case of selective repeat ARQ. And as a consequence, it is more efficient than go back and ARQ. The receiver, however, in this case receiver requires storage buffer to contain out of order frames until the frame in error is correctly received. In case of go back N, we have seen the receiver requires only one buffer. However, in this case the number of buffers required will be more than one. the sender also will require buffers more than one, receiver also will require buffer more than one. Moreover, the receiver must have appropriate logic circuitry needed for reinserting the frame in the correct order. Transmitter is also more complex because it must be capable of sending frames out of sequence, because in both cases out of order frames are to be handled. Let us see with the help of this animation. Frame 0 is being sent by the transmitter, and after receiving this frame, the transmitter is sending another frame, frame 1 now, and then frame 2, and however the frame 2 reaches the destination with error, some bits get corrupted. So, obviously the sender will send a negative acknowledgement, although the transmitter will keep on sending subsequent frames. We see that negative acknowledgement is reaching now the destination. So, the frame 2 has to be sent by the retransmitted by the sender, and before that already frame 3 and frame 4 have been sent. So, we see in case of go back and ARQ, after 2, 3, 4 and 5 were sent, but now here we find after sending 2 it sends 5. So, retransmission of 3 and 4 is prevented by using the selective repeat ARQ technique. However, here the receiver must keep buffer so that 2 can be inserted before 3 and 4. So, and also it must have little more processing capability. So, we find that in case of selective repeat, with the help of more powerful processor capability and also more number of buffers in the receiving end, the efficiency can be improved. And also it will require some limit on the window size. Let us consider the following scenario in case of selective repeat ARQ, assuming k is equal to 1, and let us assume the window size is same as go back and ARQ. Now, the sender sends frames starting from 0 to 6, one after the other. Receiver sends receive request 7, that means after receiving 6 it will send the receive request 7 after receiving all 7 frames. So, unfortunately RR7 gets lost in transit. The sender times out and retransmits frame 0. So, since it was waiting for acknowledgement for these frames, they are not received, so it will send frame 0. However, the receiver already has received all the 7 frames. It was also waiting frame 0, but not the frame 0 of the previous one, but the next one. So, the receiver has already advanced its receive window to receive frame 7, 0, 1, 2, 3, 4, 5, and so it is. So, it is now ready to receive frame 0. So, the receiver wrongly assumes that frame 7 has been lost and frame 0 is accepted as a new frame. Instead of old frame, it is received as a new frame. So, we see the problem arises here. This problem can again be alleviated by choosing a limited window size, and in this case the window size should be no more than half the possible sequence number. That means, if we are choosing k is equal to 3, then the possible window size in case of selective repeat ARQ has to be 2 to the power 3 by 2, that means equal to 4. In case of go back and ARQ, this can be 7. However, in case of selective repeat ARQ, it has to be 4. And moreover, in case of both for receiver and transmitter, we require more number of bits here, because you know that it has to be to the power k by 2. Suppose we are having a window size of 7. For window size 7, in case of go back and ARQ, the number of bits required is 3. On the other hand, for selective repeat ARQ, the number of bits required will be 4. So, for the same window size, go back the selective repeat ARQ technique will require more number of bits for numbering the frames. So, friends, we have discussed two flow control techniques, selective the stop and wait and sliding window technique, and also we have discussed three ARQ techniques, stop and wait, go back in and selective repeat. And as I mentioned, these flow and error control are performed in an integrated manner, although I have discussed separately after for the convenience of understanding. Now it is time to give you some review questions. First question is, in what situation sliding window protocol performs better than stop and wait protocol? Second question is, consider the use of 10 kilobit size frames on a 10 megabits per second satellite channel with 270 millisecond trip delay, round trip delay. What is the link utilization for stop and wait ARQ technique? Third question is, what is the channel utilization for the go back N protocol with window size 127 for the problem 3? So, in the previous case, the value of N was different. Now it was N actually it was stop and wait. So, window size was 1. Now it is 127. So, in this case, what is the utilization? Fourth question is, compare the window size, number of bits used for numbering frames and buffer size for the three ARQ techniques. Here is the answer to question number 1 of lecture 15. First question was, compare and contrast the use of parity bit and checksum for error correction. Answer is, only odd number of errors can be detected if simple parity check is used for error detection. However, simple parity check has minimum overhead. Error detection capability for burst errors for two-dimensional parity check and checksum are comparable, but the overhead of two-dimensional parity check is more than checksum techniques, as we have discussed in detail. Second question was, draw the LFSR circuit to compute a 4-bit CRC with the polynomial x to the power 4 plus x to the power 2 plus 1. As you can see, since the degree of the polynomial is 4, we require 4 flip-flops, and here you have got 3 terms. So, we require 2 exclusive OR gates connected in this manner as it is shown in the diagram. So, this is the LFSR circuit for this characteristic polynomial. This is the question number 3. Obtain the 4-bit CRC code word for the data bit sequence 100110111 using the generator polynomial given in the problem 2. Here the sequence is given, and I have already explained that how this number is divided by modulo 2 arithmetic. As you can see, first quotient is 1, second quotient is also 1, then exclusive OR is performed bit by bit, third quotient is 0. So, 0, 0, 0, so it becomes same. So, in this way we get 1011 as the remainder, which is used as CRC, and this is the quotient. Fourth question was, why the use of burst error correction is uncommon? The number of redundant bits required for error correction increases drastically as the error correction in the number of bits increases. As we know, in case of burst error, a number of bits may get corrupted. As a result, error correction is very difficult and inefficient. That is why it is not commonly used. So, friends, with this we come to the end of today's lecture. Thank you.